Hello, my name is Seung-Jun Lee and I am the presenter of this work. Our work is about applying imitation learning techniques for the reinforcement learning to virtual machine placements problem using demonstration data generated by simple heuristic. Let me start the presentation. This is the list of contents. First, I will briefly show the VM placement problem background and define the VM placement problem. Next, I will explain some background of our proposed methods and show our proposed methods and preliminary experiment result. The data center is an essential facility for cloud service. Many software like backend service for IoT or web applications is deployed to the virtual machine in a cloud computing environment. Virtual machine techniques can abstract computing resources of physical machines such as CPU, memory, storage, network, etc. By doing this, multiple virtual machines are operated in a single physical machine and can be migrated. A virtual machine can move between physical machines regardless of underlying system using migration techniques. Therefore, if you consolidate virtual machine to a single physical machine, you can reduce the number of required physical machines to operate the cloud computing data center. For example, in this figure, there are 4 virtual machines and 3 physical machines. If the 2 virtual machines in physical machine A and C are migrated to physical machine B, A and C can be turned off to save energy. According to the report below, the data center in the US consumed roughly 73 billion kWh in 2020, and about 60% of total energy usage in a data center is consumed by physical machines. In addition, physical machines consume about 70% of peak energy even when they are in an idle state, which means that they do nothing, just power on. Therefore, to reduce operating costs for a data center, we need to solve the VM placement problem to find the VM allocation method to minimize the number of used VM. If the requested resource amount of virtual machines and the capacity of the physical machines are represented in a vector, the VM placement problem can be reduced to a bin packing problem. If there is one resource type and all capacities of the physical machines are the same, in other words, a homogeneous data center, it can be modeled as a bin packing problem. If there is more than one resource type, it is now a vector bin packing problem. In addition, in a heterogeneous data center, we have to solve variable size vector bin packing, the most challenging problem among these. The bin packing problem has been proven to be NP-hard. In other words, polynomial time algorithms do not exist to date. Therefore, many approximation algorithms have been proposed to solve the problem in a short time. Reinforcement learning techniques can be used in one of those heuristics. Reinforcement learning is one of the machine learning techniques. In this paradigm, a learner called an agent does an action. The environment returns the following state and rewards that correspond to the current state and the agent's actions. The agent observes the returned state and reward, adjusts his policy to maximize rewards. Reinforcement learning is similar to human learning. It learns by trial and error. So, it could solve various complex problems that cannot be solved before, like Go, video games, and robotics. Reinforcement learning is a good method to solve complicated problems, but it takes a lot of time to learn the solutions in a large-scale problem because it is needed for an agent to interact with the environment. For example, in the AutoCAD driving problem, if you use reinforcement learning, your car agent will cause a lot of car accidents to learn how to drive. However, if your car agent imitates human car driving, The agent can understand car driving in an early learning stage, so it can boost its learning speed. This is the concept of imitation learning. Or reinforcement learning agent starts learning without doing anything. On the contrary, an imitation learning agent receives the human expert demonstration before starting the learning process and mimicking human behavior. By doing this, imitation learning can boost the learning speed of reinforcement learning. In experiment results conducted by Google, they show that the imitation DQN method reaches the convergence line faster than non-imitation DQN in various Atari games. In this work, we apply the imitation learning techniques to the VM placement problem to reduce the learning time of reinforcement learning in a large-scale problem. Originally, imitation learning requires demonstration data of human expert, but the proposed idea used the data generated by simple heuristics such as burst speed decreasing and best speed. You may worry about using a demonstration of heuristics. In other works using imitation learning, they combine A2C with imitation learning in the disaster response domain. They used demonstration data generated by heuristic too. Their experiment results show that who makes the demonstration does not affect the quality of the learning. Continuously, we selected two heuristics that can be applied to the VM placement problem, burst speed decreasing and best speed it is. Because their approximation ratio are proved, burst speed decreasing is 1.22 and best speed is 1.5. It means that burst speed decreasing returns a solution that does not use bin more than 1.22 times optimal in a worst case scenario. This figure shows the overview of our proposed method. The proposed algorithm consists of 5 steps. First, user input required data for VM placement problem. After that, simple heuristics solve the problem in advance. Aforementioned, we used burst speed decreasing and best speed. If all heuristics return solutions, convert them to demonstration data for imitation learning. Finally, imitation learning is done with the demonstration data and returns the final solution to the user. We used a modified DQN method. For solving the VM placement problem using the reinforcement learning techniques, state, action, and reward must be defined. The state is defined on a vector encoding. The utilization level of each resource of each PM and the request amount of the current VM. Action will be the ID of the PM to which the current VM will be assigned. This state and action representation is called a continuous time and event-driven decision approach. The reward is defined as the negative value of the number of used PMs and after all PMs are allocated. We define reward only at the terminal state because the required number of active physical machines can be known when all PMs are allocated. Hence, if it's not the last state, the reward is 0. To convert heuristic solution to demonstration data, generate tuples that include current state, action, next state, and reward and put it into replay buffer of DQN. This tuple is called a demonstration transaction. Next, the DQN agent starts pre-training with the demonstration transaction in the replay buffer. To show the performance of the proposed idea, we implemented a VM placement environment for reinforcement learning and DQN with an imitation component using Python and TensorFlow. DQN with imitation is a method that adds only pre-training steps to DQN among the several techniques in DQFD. This graph shows the learning speed, in other words, the number of required episodes to convergence. The solid line is our proposed method, and the dotted line is original DQ learning. This graph shows that DQN with imitation started with a higher reward than DQN at the initial episode. and reaches the neared convergence line faster. From a runtime perspective, the original DQN, which is no imitation, took about 90 minutes to converge at episode 20. Our purpose method took about 45.5 minutes to converge at episode 10 in the loading page. Plus, this method took additional 7 minutes in the pre-training phase. Therefore, the total running time of DQN imitation is about 52.7 minutes. As you see, our purpose methods can reduce running time. For another experiment, to view the only effect of imitation, epsilon for E grid reaction of DQN agent is fixed, 0.01, that is, no epsilon decay. The two experiments in the figure are results from all the same conditions, but different input data. The figure shows a similar result to the previous page. DQN with imitation started with a higher yield. Here is the conclusion. Pre-placement problem is important to save cost to run cloud platform data centers. The reinforcement learning shows good performance in this area, but if the problem size is big, show a long running time. A method for the pre-placement problem based on deep Q-learning, combining imitation learning, was proposed in this work. Experiment results show that result time can be reduced by imitating heuristics. This work will be helpful for cloud platform administrators who use the reinforcement learning for pre-placement problem. This is the end of the presentation. Thank you for your watching.